Section 2.7, two-variable inequalities. When we have two-variable inequalities, we can have linear inequalities. An inequality in two variables whose graph is a region of the coordinate plane that is bounded by a line. Each point in the region is a solution of the inequality. When we previously graphed equations, the line itself was the solution to the equation. When we deal with inequality, what we're going to do is also graph a line, but there is a region on the plane that is a set of all solutions for that inequality. When we're given an inequality, we're given options. A sign could be of greater than or equal to or less than or equal to. And that indicates when I graph the line, it's going to be a solid boundary line. In other words, it's going to look like we have in the past, just a solid line. This tells me that all points on that line are part of that solution set. I also could have a sign that is greater than or just less than, and that indicates I'm going to graph with a dashed boundary line. In other words, it will look like this. And that tells me that all points on this line are not part of the solution set for the inequality. When we graph inequalities, we want to follow this procedure. We want to copy the problem and solve for y. Number two, we want to graph by a table, slope-intercept form, or xy intercept. And we've practiced all of those in section 2.2. Number three, we want to connect the ordered pairs with a solid line or a dashed line based on the rules for linear inequalities. In other words, solid would be greater than or less than or equal to, or dashed would be just less than or greater than. Number four, we want to select a point on either side of the line. This is your choice. And we want to substitute that into the original equation. If the inequality is true after substituting, then we want to shade on that side of the line from where you selected the point. If, however, the inequality after substituting is false, then you want to shade on the other side of the line from where you selected the point. Let's graph this inequality. Y is greater than a negative 1/3 x plus 2. Recall from our previous sections that y equals mx plus b, slope-intercept form. Here I know that my slope is a negative 1/3, and my y-intercept is 0, 2. I can use this information to graph the line, and knowing this information that it is greater than, I know that my line is going to be dashed. Graphing my y-intercept 0, 2, and counting with my slope. Since it's negative, I'm going to go down 1 and to the right, 1, 2, 3. Down 1 and to the right, 1, 2, 3. Connecting the ordered pairs with a dashed line. Now I select a point on either side of the line. I'm going to select the easiest one, which here is 0, 0. So I selected a point that's not in the line. 0, 0, x is 0, y is 0. So when I substitute, negative 1/3 x plus 2. Y is 0, I plug in a 0. X is 0, I plug in a 0, plus 2. Simplifying, I get 0 is greater than negative 1/3 times 0, 0, plus 2 leaves me 2. 0 is greater than 2. That is false. Therefore, all points below the line are not in the solution set of that inequality. But I do know when this is false on this side of the line, then all points on the other side of the line, or region, are solution sets of the inequality. And this region identifies all points that are solutions to that inequality. That does not include any point on the dashed line. For our next example, we want to graph x over 2 is less than or equal to a negative y plus 3. I'm going to flip this around, so I'm going to have a negative y plus 3, and on the right side I'm going to have x over 2. In this type of situation, I know that x over 2 has to be less than this quantity. So I'm going to mark my inequality the same way it is in the original problem. So in other words, a negative y plus 3 is greater than or equal to x over 2. Now we want to solve for y. So I'm going to subtract 3 on both sides. That gives me a negative y is greater than or equal to x over 2 minus 3. Now I need to divide both sides by a negative 1. That gives me y on the left side. On the right side, this has to go into both. I could have multiplied on both sides also, which gives me a negative x over 2 plus 3. Recall that it has to go into both quantities. Also recall that when I multiply or divide both sides by a negative 1, I must flip the inequality. So this becomes less than or equal to. Now I'm going to use the slope-intercept form, y equals mx plus b, and I'm going to graph this. So here I have a slope, which is m, to be a negative 1 over 2, a negative half. My intercept is 0, comma, b, which is going to be 3. I'm going to graph my intercept, 0, 1, 2, 3. Then I'm going to graph my slope, which is a negative 1 over 2. Since it's negative, I'm going to go down 1 over 2. Down 1 over 2. Now, I want to go back up to my problem, and I realize that it is a greater than or equal to or less than or equal to. Therefore, I know that this is going to be a solid line. I pick a point on either side of the graph. Here I'm going to select 0, 0 because it's not on the line and it's the easiest point I can select. When I substitute in, I'm going to get 0 over 2 is less than or equal to a negative y, which is 0, plus 3. That gives me 0 over 2, which is 0, is less than or equal to 3. That is true. Therefore, I'm going to shade on the side from where I selected the point. The point was below the graph, therefore I will shade below the line. And this shading represents all solutions to the inequality, and since this is a solid line, it includes all points on that solid line. Next, they want us to graph 4x plus 2y is less than 4. Here I'm going to solve for y, so I'm going to subtract 4x on both sides. That gives me 2y is less than a negative 4x plus 4. Divide by 2 on both sides. That's going to give me y is less than, 2 goes into both, whether it goes into evenly or not, but it does here. So this is going to give me negative 4 divided by 2 is a negative 2x. 4 divided by 2 is a positive 2. Slope-intercept form. So my slope is equal to a negative 2, and I also can write that as a negative 2 over 1. And my y-intercept is 0, 2. I graph the intercept 0, 2. My slope is a negative 2 over 1. So I'm going to count down 2 to the right 1, down 2, and to the right 1. I go back to the problem and I realize that I am dealing with just an inequality of less than. Therefore, this is a dashed line. And then what I want to do is select a point that is not on the line. The easiest point to select is 0, 0 again. And when I substitute it into the original, I'm going to get 4 times 0 plus 2 times 0 is less than 4. That's going to give me 0 is less than 4. That is true. Therefore, all solutions are below the graphed line. So the shading represents all solutions to the inequality, but does not include the points on the dashed line itself. Here they want us to graph a negative 4x is less than or equal to 4. When we only have one variable, it's easier to create a table. So let's solve for that variable, and then we'll generate a table and graph. So here, I'm going to divide both sides by a negative 4. When I do that, I'm going to get x, and on the right side, a negative 1. Also recall that when I multiply or divide by a negative value, I'm going to flip the symbol. So this is going to become a greater than or equal to symbol. Now, what I do is I create a table. Here, x is a negative 1. So in all situations, x has to be a negative 1. And then I create a choice for my y. I usually pick the easiest one, 0, 1, and 2. Then I graph my ordered pairs. Negative 1, 0, negative 1, 1, and negative 1, 2. And I also know that my inequality is a less than or equal to or greater than or equal to. That generates a solid line. And from previous sections, I do know that when I solve for just an x, that creates a vertical line because I'm just going to intersect the x-axis. If it was a y variable, then I would just create a horizontal line because it would be intersecting just the y-axis. Now, I still want to follow my same procedures. I want to pick a point on either side of my line. Again, I'm going to pick 0, 0 because it's the easiest. So when I pick 0, 0, I substitute into the original equation a negative 4. X is 0 is less than or equal to 4. And what I get is 0 is less than or equal to 4. And that is true. Therefore, I shade on the side where the point came from, since it's true. So that would be on this side. So this shading represents all solutions in the region that solve for this inequality and includes all the solid points on the line. Now, if we go back and take a look at each one of these past problems, you can see which side I shade on just by the inequality. Here, the x values have to be greater than a negative 1. Notice this is where all the x values are greater than a negative 1. On the next problem, I see that I have values y is less than a negative 2x plus 2. Therefore, I need all y values that are less than that, and that's why I shade below it. Picking the point is another way to do that, and that's what we've been doing, but you can also do it by the inequality. On the previous problem, I have y is less than or equal to a negative x over 2 plus 3. Again, I shade below the line because y is less than or equal to. Here, we've already done this problem, but I know if I did graph this again, I would graph the area or shade the area above the line because y is greater than that value. Another example. A restaurant has only 15 eggs until more are delivered. An order of scrambled eggs requires 2 eggs. An omelet requires 3 eggs. Write an inequality to model all possible combinations of orders of scrambled eggs and omelets the restaurant can fill till more eggs arrive. Graph the inequality. Well, here I'm going to let x represent people ordering scrambled eggs. I'm going to let y be the number of orders for omelets. Now what I'm going to do is generate the inequality. Well, how many eggs are required when you order scrambled eggs? That's 2 per order. And how many eggs are required when you order an omelet? That's 3 per order. Now, no matter how many scrambled eggs or omelets are ordered, they have to be less than or equal to the number of total eggs that we have, which is 15. So this is the inequality that represents how I can order eggs in that restaurant. So now all I need to do is solve for y. Subtracting 2x on both sides, I get 3y is less than or equal to a negative 2x plus 15. Divide by 3. That gives me y is less than or equal to a negative 2/3 x plus 3. My slope, we know, is going to be a negative 2/3. My intercept is going to be 0, 3. Now I graph. 0, 1, 2, 3. It's negative, so I'm going to count down, and 1, 2, 3 to the right. Down, 2, and 3 to the right. And this is going to be a solid line because it's less than or equal to. And I need to shade. And from our last directions, I need to have values where y is less than this line. So that would represent all values here, including all points on the line. Now, we can verify that by using our past procedures. And I could select 0, 0, again, because it's not being intersected with a line. So if I use 0, 0 and substitute in, I can get 2 times 0, which is 0, 3 times 0, which is 0. So that would be 0 is less than or equal to 15, which is true. And notice, this point is on the side that I shaded. Therefore, the procedure does work. On this example, they want us to write an inequality for each graph. The graph is given, and also we're given an equation that represents this graph, but they want us to write this boundary and dashed line as an inequality. We know that I'm going to have my value of y. On the right side, I'm going to have a negative 3/4x plus 3. I need to determine if this is going to be a less than or greater than, and also determine whether this is going to be less than or equal to or greater than or equal to. Here I have the line graphed, and I'm graphing y values below the line. Therefore, I know this is going to be less than. As we've seen on our past examples, we can pick a point or we can take a look at the inequality. Since I'm having shaded areas below the line, that means y is going to be less than this graphed line. I also know that this is dashed. Therefore, I know that this does not have an equality to it. So this is my solution for the bounded area. Here, we're given a horizontal line, y is equal to 4. And I have my shaded area above the line. So again, I have y, I have 4, and since this is being shaded above the line, I have y values greater than this line. So therefore, this would be greater than. Since this is a solid line, that's going to give me an equality factor to that. So my solution is y is greater than or equal to 4.